Oh, Jordan. Hello, Jordan. Can you hear me?
Yes. Can you hear
Nice.
me?
Yeah. Yes, I can. Yeah. I saw your email yesterday. Thanks for responding. That was good. I was glad to know that it was working. Yeah. But you were up at 3:30.
Yes. You were up at 3:30, huh?
Yeah. But I have these odd hours. I keep odd hours. Yeah. The only big deal was that I was coming from the other side. Otherwise, I wake up early.
Oh, okay.
Ridiculous. Yeah. But this time I was sleeping late. Yeah. So it was not my usual stuff. Yeah. But I often do it.
Same. I'm up late
Yeah.
a lot because whenever I get off work, it's hard to just go right to bed.
Got it. Yeah. So are things getting worse in the last week? Probably yes, right?
Uh, it's been about the same, but still
Okay.
very busy.
Mhm.
But it should, when all this stuff is over, everything will feel much better. But for now, you just gotta take what life gives you and deal with it.
Yeah. I think that's I surely agree to that because we don't have any control on it. So why talk and make it worse? Yeah.
I agree. No control.
Yeah.
So just
Yeah.
live with what you got and enjoy life when you
Yeah.
can.
Exactly. Yeah. I think that's a right spirit. Here we have Avinash coming in. So till now, no broken links, right? In the website that I gave you. Yeah, as far as the simple, immediate ones work, that's good enough. Because I didn't test much.
I didn't test all of them, but I clicked
Yeah,
on
of
4 or
course.
5 links and
Yeah, same thing. That's what I did. Yeah. Usually, since it's just a copy of the whole thing, it shouldn't. It's not error prone. So, so it should be okay. Hello, Avinash.
Good morning.
morning.
Let's see. Where are this? Oh, I should check. The department page is still down, I suppose, when I checked last time in the morning. An hour ago. Yeah, still down. And I haven't heard from Bob. So it worries me a little because in these times when you don't hear from someone, when you're used to hearing from them pretty immediately, think that, oh, they're sick or something.
Yeah. Hopefully that's not the case.
Maybe he's in a vacation or something.
Yeah, that is good if that is the case. Yeah. Okay, where is Angela? Where is Moses? How are you, Avinash?
I'm okay.
Have you got
Health-wise,
brighter than
I'm okay, but academic-wise, not really.
Yeah, it's amazing how these things can tumble things down.
It would have been a lot better if it was just like a month or a couple weeks. It gets worse with time. Doing a whole semester like this would have been just horrible.
Yeah. And I would think that people will even think twice before enrolling in those kind of situations.
Yeah.
I don't think people are just here for grades and other things. There is, I do feel
Good
that
morning, everyone.
socialization also. Hey, Angela.
Good morning.
Angela.
Hello, Moses.
Good morning.
Yeah.
I was just reading a news article, and they're saying New Jersey might not reopen the schools until fall of 21.
Fall 21.
I was just reading a news article.
Well.
Surely that wouldn't be the case.
Yeah.
It's a possibility. They're saying it's not going to happen, but they're considering. Who knows?
Yeah.
The CDC director said, "Hey, it might come back in fall with with deadlier thing, like deadlier mutation, and we might have a second wave."
Yeah,
All
let's
things
wait
on the
and see.
table.
Yeah, let's wait and see. I don't think we should speculate. We should. That's too far a speculation. I feel it at this point. Yeah. Hopefully, but who am I? Okay. So everything going good, Angela, Moses?
Yeah. Okay.
Yeah. So I did make a new page for us. I think that should be sufficient for, hopefully that also doesn't go down, but it shouldn't. I think that will be unlikely. Yeah. So let me know if there is some broken links in there. There is a chance that something might not work. It's a exact copy of what I usually use as our my page, but still where it is hosted from, that it might have some functionality that depends on that. In that case, there might be something that's missing, but as of now I couldn't see anything, and yeah, but I didn't check it sufficiently. Okay, so so again, we have homeworks. Let me change the camera. So yeah, I should point out that there's a new website, right? So that's oh, what is my website? I forgot my own website.
S physics.
No, it's not as physics.
Shows sphics.com. That's the main website.
So I made it out of spherical harmonics. The first three letters of spherical, and then harmonics. So the last three letters of harmonics. I couldn't be more. I thought a little, but then I didn't have so much time to worry about what name to choose. But so that's how it came about. Yeah. So that's the spherical harmonics. So that's it. So anyway, so we have homework 9. That is the only thing remaining, right? Which is officially due April 30th. That's a Thursday, but unofficially due by the exam date. Right?
I forgot which date.
Which is when? The unofficial.
Oh yeah, so everything is due. Like everything due on what is it? Final exam is, oh, it works well, May 8th. May 8th, Friday. Let's make it 10:15 so that you guys finish it on Thursday itself. Again, it's not strict. Let's say 12:15. p.m. Okay. It's not really strict, but and don't make it right until that point. That would be a lot of work for me that I had to grade everything in the 24 hours. So whenever possible, whenever you finish things, start sending it in so that I have room to put things on the grade book and all that. So, but go by your convenience. Yeah. Okay. So any other comments or anything relevant? Okay, so we want to do special relativity. So this is the conventional. I motivated it hopefully to good extent last time. This time we want to see the actual equations that govern special relativity. So we will go in the traditional way of Newtonian physics. First define time, then define position, and we'll combine them. So that will be the new part in special relativity. So that space and time work together as an invariant. That is an invariant structure to that. Then construct what is velocity. Velocity in Newtonian physics is rate of change of distance over time. It will be the same thing here, but we are looking for some fourth quantity which together with velocity has an invariant structure to it. Right? We are looking for something that does not change under Lorentz transformation. Same thing, then we go by acceleration, do the same thing. Acceleration is rate of change of velocity with time. But what is the fourth quantity that behaves that conspires together with the acceleration so that there is an invariant quantity? So let's see that. So broadly, so let's call it relativistic kinematics, right? That's what usually I call this. Oh, I should say that, point out a couple of you, so we are only 4 of us, right? Half of you basically have taken either my graduate level E&M or undergraduate E&M. This shows up in some form or the other. Mostly this part will be a repetition. The earlier part was not. There are various ways you can motivate special relativity. You can reach the same place, either you starting from Maxwell's equation or starting from the relativity principle. So here we have started from the relativity principle and reached here. But from this point on, the equations they're reasonably the same, except for some minor changes in motivation, I suppose. So we'll define what is called a 4 vector. So this is going to be a 4 position vector. So 4 position, let's say. Okay, so that's our starting point. And we will use the notation x mu. This is sometimes I'll call it upstairs mu. It's basically contravariant vector. So it's important that it's in the superscript. So the index mu is in the superscript. Remember, we already said mu runs from 0, 1, 2, 3. So there is a 0th component. The 0th component is going to be c times t. We put a c so that it's basically time, but we multiply with a c so that it has a dimensions of distance. Right? And the rest of the 3 components is going to be x. So that's so 0 is time, 1, 2, 3 is the usual spatial component. We will also understand that there is x mu, the subscript, and that will be the covariant vector. And that's simply got by changing the sign of the 0th component. That's good. Based on this, we can define an invariant distance. So that will be the length, or the various languages used, an invariant distance which is the same as the length of the 4 position in the Lorentz transformation we are talking about. So this will be, you can simply say this is the magnitude of x mu square, but more, it is more standard to say this is x mu, right? One is in the superscript, one is in the subscript, and you basically multiply these two, right? Multiply the superscript and the subscript as if you're taking the dot product. Like in rotations, you do dot product. Here also you do a dot product, but with the negative sign into, taking the negative sign into account. And so this will be equal to minus c square t square plus x dotted with x. So this negative sign shows up. Okay, that will be the generic idea we will be using. Okay. And this element, this length x mu, if you want to really talk about length, it is the square root of this. This remains the same. It doesn't change whether you're in any of the local Lorentz frame, or let's just say inertial frame. Pick any one of the frames that is going with constant velocity. With respect to that, this quantity will remain the same. If you were to measure the position with respect to some origin, I haven't specified the origin here, measure the distance x, measure the time t with respect to some origin, that quantity will remain the same whoever, whichever inertial frame measures this quantity. So that's the idea we are using. Okay. And of course, this can be, this distance can be greater than 0, less than 0, or equal to 0. And we talked about it to be space-like, time-like, and light-like quantity. We can talk in terms of differentials in this case. And then what we get is, it's an immediate thing. You can start with x dx mu. Right. Instead, we will say c dt, and we have dx, right? So this is the differential element of the position, or the change in position with respect to some quantity. It is not with respect to time. It could be with respect to time also, but it is any arbitrary change in the displacement in time and in displacement and position. This squared quantity, we give it a special meaning or special name to it, or this will be useful for us, and that will be minus c square dt square plus dx dx. Okay, and let's see, and this quantity we will call it, what do I want to call it, minus or plus, I'm thinking. Let's call it minus ds square. Okay. And again, the same thing stays. This can be positive, negative, or 0. So that's all the possibilities. So instead of talking about the whole space-time, we are talking about a really small point, and around that, everything, all the same ideas work. It could be positive. The change, small change could be positive, negative, or 0. That's good. So that now we have a tiny element here. So the point, the difference here is that, so next point is we would like to talk about 4 velocity, right? And at this stage, now we would like to, in principle, talk about dx by dt. So our usual velocity will be the same. So this is our usual velocity. No difference in that. The small change in position divided by small change in time, that still stays. But we know that that's not an easy thing to work with, because dx changes from observer to observer. dt changes from observer to observer, or observer means the inertial frame to inertial frame. So what do you mean by velocity in the way this is constructed? Of course, velocity is there, but this might be changing from observer to observer, which is what we know how it changes. So we would like to define our forward velocity not in terms of that, instead with respect to ds, because this is an invariant quantity. This doesn't change between observers. So why worry about that? We will change it with respect to this, but still physics will be done in terms of velocity. So don't forget that the physical quantity which we understand is still going to be the velocity, but that is a more more elegant situation, you can say, or more comfortable situation when you're comparing between people. Then you don't have this complication that, oh, how does the numerator change, how does the denominator change? It can be done, but we don't want to go through that whole process. So this is much easier. So for that, we construct what is called the forward velocity, and forward velocity is going to be defined by, so let's say u, it's the same mu, but mu and u actually is going to be a little off, right? So let's call it alpha. It doesn't matter whether I call it alpha to begin with there. So it doesn't matter whether it's mu or an alpha. As far as it runs from 0, 1, 2, 3, that's good enough. So u alpha will be so this will ds often will be called the proper, so how do you say this? So ds can also be thought of as c times d tau. So there are various ways you can define it. So ds here will be proper distance, d tau will be proper time. So some invariant distance if you want. Let me not specify it to be proper time or proper length. Invariant distance, I think that's the nice way to. I don't want to call it proper length because it has a negative quantity here, and length has a positive quantity there, right? So it has a time feature to that. So I don't want to call it an invariant length. Time, I don't want to call ds an invariant time because it doesn't have a dimension of time. So d tau is the right thing to talk about, but I'll be working with ds. So let me use the word invariant distance. But the idea is that there is something that is invariant, one of those quantities. So it doesn't matter what exactly it is. So it will be defined as dx alpha, like all the four quantities change now, divided by ds now. But then I have to be a little careful because now the dimensions are not of velocity. If we are talking about velocity, so I want to keep the dimensions the same. So this is distance in the numerator, distance in the denominator. So I multiply by a c there. So that's going to be my forward velocity. And by construction, I don't have to worry too much. By construction, this has to be, the length of this quantity has to be the same in every reference frame and which every inertial frame. And we will show that that's actually the case. But first, let's evaluate what are these quantities. What is actually the components of this? This is ds, right? Not dt. So let's try to think about that. So that's sort of comes out straightforward. So let's, oh, I still have space, no, almost. So, was I on the other board till now? Or did I move to board number 1? It was visible, right? Okay, sorry. Okay. So that's equal to, since we know how velocities work, so we still want to write everything in terms of velocity. So let's change ds to dt. So this is dc times dt over ds times dx alpha over dt. Right, that's a chain rule, and that makes it c times dt over ds. Dx alpha by dt is d by dt of c times t. That's the 0th component of the position 4 vector, and d by dt of x. Right, that's the spatial components of the 4 position, and with respect to time now. But now this is velocity, right? And this one is easier derivative of time with respect to time is 1, so it's just c that remains. So apparently this is equal to c times dt by ds times c and velocity. So if we know what derivative of the usual Newtonian time with respect to the invariant distance is, we actually know what 4 velocity is. So let's go about and let's calculate this dt by ds, which is almost there here immediately, right? So let's look at that. Okay. Any questions here as of now? Okay. Yeah. Okay. Okay. We want to find dt by ds, but we do have this minus ds square is equal to minus c square dt square plus dx dotted with dx, correct? Pull this out. So this is minus c square dt square. Like these are differentials. If you don't feel comfortable about working with differentials, make it a difference, and in the limit something going to 0, right? That's the way differential and the differences work. So if you don't feel comfortable with differentials, change it, make it into differences and take the limit. This is 1 minus 1 over c square times dx dotted with dt. Like again, these are differences, and then you take the limit, dt tends to 0, so that becomes velocity then, right? Dx by dt is velocity. And 1, so this is minus c, or let me write, so negative negative cancel, so we suddenly have ds is equal to c dt times square root of 1 minus v square over c square. And that's a familiar quantity that shows up again and again. That's almost a signature of relativity, is that if we were to call beta to be, beta is a vector velocity over or scaled dimensionless quantity representing velocity, and gamma, right, is equal to 1 over 1 minus beta square root of that. So that's 1 over gamma. So bring that down on the left. So we have gamma is equal to c times dt over ds, right? Which is exactly the quantity coefficient that's sitting in the 4 velocity that we defined. So we can write our 4 velocity as u alpha is equal to gamma is there. So it is c times gamma and velocity times gamma. Right? That's gamma. It looks like new in this way of writing here. Okay. That's, again, velocity is the important part. For velocity, what does it mean? It is useful for calculating an invariant quantity associated with velocity. That's the importance of 4 velocity. Otherwise, 4 velocity itself is not significant at this point. And we'll see, in a sense, it is significant because it's used to define your momentum in a sense. That's good, but we are saying that, okay, velocity is not invariant, gamma is not invariant under between inertial frames, but the length of this quantity apparently is invariant. So look, it's good to calculate what is its length, right? What exactly is this quantity? Any guesses what it will be? What will be the length of this quantity? Like something associated with velocity that doesn't change between inertial frames.
Speed of light.
Like speed of light, right? That's the velocity that doesn't change with respect to anything. So maybe this will be speed of light, but let's see what it comes out to be. So
Should it
for
not be
calculating
negative
the
of
length,
C?
tell that again.
Should it not be negative of C square?
Yes, negative of speed square. That's correct. That's correct. But the length itself, you would take the square root of that, and for that also you want to remove the negative quantity. So yeah, both answers are correct. So technically, the length will be square root of the squared quantity. There also, since there is a minus sign sitting, so there's a chance of imaginary quantities coming in. So the idea is that absolute value of that whole quantity is there. But there is a feature of time-like, space-like, and like-like feature also there. But yeah, correct. Technically, to answer the question, it's length square here that we'll be calculating. That's negative C square. And we'll talk about the negative, what does that negative mean in a few minutes. So let's, again, calculating the length is relatively easier. In special relativity, we just have to change the sign of the zeroth component of the 4 vector. At this stage, it is good to point out that if you were doing general relativity, this switch is not easy. Okay, this is a whole transformation that comes with it. Here it is just a minus sign that is changing. That's a whole transformation that will sit in there, a very arbitrary transformation. So it's a very complicated structure that shows up immediately. That's the only big difference, and that's what usually is called the metric. Oh, maybe I should think I have to. So this is called the metric. So you have this ds dt square. This is the metric. This is a metric for flat space. Okay, because length, remember what does it mean by flat space? If you draw a triangle, the sum of the angles is 180 degrees. That's a simple signature of flat space. If it is curved like a sphere and you draw a triangle on it, the sum of the angles can come out to be larger than 180 degrees. And if you draw a triangle on a hyperbolic surface, then the angles can be less than 180 degrees also. And that feature shows up the moment you deviate from here. Right? For example, as simple as you can add something here, or you can put a function here. It could be anything. Currently, this is 1 here and minus 1 there. That's the simplest you can get. You're saying that distances are taking, you can say, symmetric positions. Right? If it has 2 dimensions, x and y have a lot of symmetry in them. But if you have a curved surface, then x might scale a little more than what y might do. So that's the way to look at a curved space, which probably, since some of you will be taking math methods with me, we address it a little bit in the math methods course in the beginning, but it's a very little bit. We don't get the time to go full into that. I had earlier said that I might do a little bit of general relativity, but I don't think I will have the time to do that at this point. So we'll have to postpone in another discussion somewhere else, some other place. But that's a small promise I fulfilled there, that the metric I introduced at least. It's a flat metric. Okay, so coming back to the length of this vector, so you simply multiply u alpha, correct? And that is, immediately you see that, oh, minus c square gamma square plus v square. So it's gamma square. If I were to pull out a minus c square, I get 1 minus beta square times gamma square. And gamma square times 1 minus beta square is exactly equal to 1, because gamma square is 1 over 1 minus beta square. So that's minus c square. And that's what Avinash pointed out, that this will be negative quantity and a c square. And c is a constant in this whole construction that we made, we began with that postulate, right? It's not that it turns out to be a constant. In fact, we required it to be a constant. We said that we want a relativity in which C does not change with time, because Maxwell's equations did not have C changing with time. So we almost imposed it actually. So that's what shows up here. So velocity actually is a component of this 4 vector, which comes together with this factor gamma, and they all transform. Gamma transforms, velocity transforms, but this length of this 4 vector minus C squared does not change. And since it is minus, that clearly says that U alpha as a 4 vector is a time-like quantity. Right. So that means to say, so is a time-like 4 vector. By 4 vector, we mean in the Lorentz space, it can be represented in that light cone. What is the relevance of that? At least in the practical sense, that means there exists a frame, there always exists a frame in which you can pull this out, right? So you can get rid of the space completely. So there always exists a frame, U alpha, where it is purely time-like, and so that is C. So this V is 0. So whenever you say time-like, the first thing that should come to your mind is that there exists an inertial frame in which, if you measure this 4 vector, it doesn't mean that you're measuring the particle's velocity. This is nothing to do with particle's velocity. Particle velocity also sits in it as part of it, but there exists a frame in which this 4 vector will be exactly purely time-like, which means to say the length of the vector shows up as the time component alone, and that's C comma 0, right? What else did I want to say on this? Which is that frame? Which particular frame is it in which this 4 vector looks like this? Like, which frame is it? Is the question clear? Like, there are lots of frames, right? Something going with 1 meter per second, something going with 2 meters per second, something going with 3 meters per second. This is the 4 vector associated with a particle moving with velocity v. In which frame does this become this?
Rest frame.
Is the rest frame, because if I set velocity v equal to 0, this spatial part immediately goes to 0, and gamma is 1 because 1 over 1 minus v square over c square, v is 0, gamma becomes 1. So that becomes this. So if you sit on the particle, so whichever particle you are describing this 4 velocity with, and if you sit on the particle itself, in that particular frame, its 4 velocity will look like this. And if you were to measure the length, then it is very easy because it is just one component, right? When you take when you're doing vectors, it is significantly easier if there is a single component, and that's length is minus c square. So that's some part that shows up there. Any questions at this stage? Okay, so that's good. So we have 4 position, 4 velocity. Again, the motivation is that what are the quantities that's that together have an invariant distance associated with this. Once we have the 4 velocity, it's almost immediate to talk about 4 momentum. So this involves a small input here. So as of now, everything followed from one to the other, correct? So now we introduce a new idea. So this is mass, right? M. There's a mass M. And we say this is an invariant quantity as to begin with. So M doesn't have any dependence on this on any of this frame. So this is an invariant quantity. So invariant quantity to begin with. And we define 4 momentum as pretty straightforward. P alpha will be just mass times U alpha. Right? That's what you do in Newtonian physics also. Mass times velocity is 4 momentum, but we are going to make a small change here. This step is what changes between relativity and Newtonian physics. That's a big step. Rest everything remains the same. So we'll do that in a minute. This is equal to, if I were to use the idea of for velocity, this is mass times c times gamma, and this is mass times v velocity times gamma. Right? Since we developed the idea of 4 velocity, it is simply multiplying by mass, nothing different here. Correct. Okay. So let's now, so this is now the physics part in here. So this is if you want the postulate, right? So this is the physics coming in. This is what you can associate Einstein with. This was not obvious to see, but he could actually see that this was necessary to put everything in order. So this is a new change now. So this is P alpha MC gamma, just copying again back. So this is MV gamma. Now, this is now related to, remember, this will be your momentum, right, in your Newtonian physics. So let me call that P, we will never use this. Okay, so this is going to be P Newtonian. So forget the Newtonian momentum from this point on. See, velocity remains the same in relativity or Newtonian physics. It doesn't change, but momentum and energy's definition changes. So the energy and momentum is no more going to be our old Newtonian quantities, but this is the definition of energy. So this is E over C. Whatever this is, the 0th component of momentum is going to be energy, and for dimensional reasons, you divide by C. And the spatial components, by spatial components, I mean the 1, 2, 3 components of the 4 momentum will be defined as to be the momentum. So don't get confused between this P. We will always use P with the definition that it is MV gamma if you're in relativity. If you, in this context, if we ever have to discuss mass times velocity, the old Newtonian and quantity, then we say that is MV. So from this point on, P means MV gamma. And that's the physics coming in. So this is E is equal to now MC square times gamma. And which is, if you want to explicitly write this, this is MC square times 1 minus V square over C square. And you can always ask, which energy is this? Is this a kinetic energy? Is this a potential energy? We haven't talked about any potential energy. There is no interaction. There is just one charge or one particle moving. So it's basically the hopefully the free energy associated with motion. But what we are going to see here is that it's not just energy associated with motion, which is what we usually say is kinetic energy. That is going to be an energy associated just being at rest too. So just having mass itself amounts to energy. That's the new thing that comes up in special relativity. We'll see that in a few minutes. Right? And P here, momentum, is defined as mv gamma. Now that's mass times velocity over 1 minus v square over c square. That's new. Like this is this connection is a postulate if you want. Right? So this is not, we haven't derived this from anywhere. That's coming. That's a connection you make, and that's what Einstein contributed, or he developed the whole thing. But that was the most important equation, if you want, which leads to the whole physics that we do. Just with those two equations, you can do whole of special relativity. Okay, so this is good. So now we have a new energy, new definition of energy. You have a new definition of momentum. This should somehow, in the small velocity regime, go back to your Newtonian physics, correct? So that should be the case. Always the limiting conditions should work. And let's see how that works. So let's begin with momentum. That's an easy part. So somehow this should become the Newtonian momentum for small velocities, right? So let's begin with P. The standard momentum, which is mv. I can write this as 1 minus v square over c square raised to minus half. Correct. That's a binomial expansion. Expand it out. So let's say v is very much significantly smaller than speed of light. And then I have mass times velocity. You expand this. So this is plus half v square over c square plus higher orders. But if velocity is smaller than speed of light, typically, even if you talk about the speed of Earth while it is going around Sun, that's about 10 raised to minus 4. And if you square that, that's 10 raised to minus 8. That means it's the 8th decimal that is going to change with respect to 1. So you have to be doing an experiment with 8 digits of accuracy in that measurement, which is about 1 in more than a million, right? Almost 10 in a billion. That's very hard experiments to do. But yes, there exist experiments which can do that. In fact, these days, even GPS, for GPS to work correctly, because it has to travel such a long distances, even a small error contributes significantly. So these quantities do play a role. But most of the experiments that we do, especially that we do in our undergraduate lab, that is 10% accuracy is great enough. And this here we are talking about 10 raised to minus 8. So that's significantly small. So if you were to neglect that, so that's equal to mass times velocity, which is the Newtonian momentum, right? So this is P Newtonian. We don't introduce a new definition of P. So sometimes in the early stages, there could be a confusion that, oh, P, we are used to mass times velocity. No. In relativity, P is always mv times gamma. Okay, so that's a change that comes in. Okay, any questions? Okay, so let's do the same thing with energy also. So energy is mc square times 1 minus v square over c square times minus half. Same idea. And let's keep the leading order, right? First, like have the leading order and get rid of everything else that is small. But now there is a small difference. So if you were to expand this, this is mc square. And you have 1. Again, this is plus 1 by 2 v square over c square plus higher order terms. But now you cannot drop this v square over c square, notice, because when I multiply with mc square, the c square cancels out. In fact, the second term also is significant. It could be large, right? But you can always say that mc square is going to be so large that even the kinetic energy is going to be small. And that is the case in non-relativistic case. So let's write this down. So this is mc square, right, plus half mv square plus quantities that are significantly smaller, right? But now notice, if you're doing usual relativity, then these two could be comparable, these two terms. And you usually say this is the energy associated with being rest. You don't usually have an energy associated with being rest in Newtonian physics. If you're at rest, there is no kinetic energy, so it's zero. But this is what is called the rest mass of a particle. Just because the mass exists, that is an energy. And this leads to the idea that what if you change the mass? And where does it change the mass? Remarkably, in the same period of time between 1895 and 1905, people discovered radioactivity, exactly the same time. And what is radioactivity? Radioactivity is the idea that mass changes from one element. When you change element, suddenly, miraculously, suddenly the mass can disappear, right? And if mass disappears, energy disappears. Where does it show up? It shows up in energy. And that's the idea of radioactivity. When we think of radiation, when there is radioactivity happening, that energy is coming from this piece, mc square, because the mass, rest mass of something is changing. And this is what then eventually led to the idea of atomic bomb in the 1943 it was developed, I guess. First time it was executed, but then it was used in a real population in 45. Horrific, but a very important idea. Like very horrific, but still very I mean, the concept is very different. So that's half mv square. But again, notice, what do you do in usual physics then, usual Newtonian physics? What is happening is that this is a big quantity. Like if a typical mass velocity is significantly smaller, this is significantly larger. But what you do in Newtonian physics is, it is large, but it stays the same, right? It doesn't change. And we talk in terms of change in energy usually. So that is sufficient. Half mv squared is good enough. But this is supposed to be there in principle. If you're doing Newtonian physics, mc squared is sitting there, but that's a constant all the time. So you just subtract it out. So it is there, but it doesn't play a significant role because it's a constant. So half mv squared, so kinetic energy K is identified here as half mv squared. And rest mass, what will you call it? So yeah, rest mass is rest mass. Let me not define any letter associated with this. Okay. Any questions here at this point? There's one more thing we can actually do here. So let me actually use this space itself here. I can probably squeeze it in here. So this is mv, which is p Newtonian. That's what we showed. That's good. So for momentum is, if I were to go up now, yeah. For momentum is energy and spatial momentum, and that is also equal to mu alpha, right? So this is mu alpha. So it's natural to ask, what is the invariant length associated with for momentum? Correct? What is the invariant quantity? We know that momentum changes in a process. When you have a collision, momentum changes, energy changes. Like that's how we would define elastic collision. Elastic collision deals with kinetic energy is conserved, momentum is conserved. Those are the processes. But apparently here, there is an invariant distance which doesn't change. Whatever you do in a collision, there is some quantity that cannot change at all in that. And it's interesting to ask what that is, but that's easy now because P alpha is equal to mu alpha u alpha that we already calculated, right? Mu alpha times m alpha. U alpha is minus c square we saw. So that's minus m square c square. Right. So energy and momentum do not remain the same. If you go from one inertial frame to the other, you will measure different kinds of momentum. Like if you measure momentum to be 3 meters per second times kg in one frame, it might measure 300 kg meters per second in another frame. But what will remain same is this quantity, which is mass basically. If I were to divide out by c square everywhere, it's basically mass. So mass is what remains the same in between the inertial frames, and which is what we began with, right? When we defined P alpha for momentum as mass times U alpha, we said that mass is not going to remain change, and that's what shows up again. I didn't have to say that there. Whatever comes out here, I could have defined it to be the mass, and that would have been a much more natural definition for mass. So what is mass now in this way of saying? So P alpha is also equal to minus E square over C square, right? Because E over C times minus E over C plus E dot P is equal to minus M square C square. And let me again squeeze things here. So let me say this is E. So this equation, if I were to multiply out with a negative sign, get the C square at other places. So E square is equal to P square C square plus M square C raised to 4. Right. Often you will write this as a square root, and if you're in the rest frame, only if you're in the rest frame, in the way we have defined things, in the rest frame, E is equal to MC square. But this equation is so popular that you would like to involve a lot more into it than what we have said. It's only in the rest frame that E is equal to MC square. So often what in the elementary level textbooks you do is that you change the definition of mass itself and say that this is actually M effective, if you want, 4. And then this will be M effective. So then you don't have to go into the rest frame. So this is M effective C square. But I will completely stay away from that. Let's stick to the idea that mass is the invariant quantity associated with energy and momentum for vector. So this is often called the 4 momentum, or will also call it the energy momentum for vector. Okay. Any questions on this? Okay. So that plays an important role. These two are the, if you want, you can avoid the whole 4 vector definition idea of 4 velocity, 4 vector, and just begin from here. Like that's sufficient. What is the energy in relativity? What is the momentum in relativity? And that's it. And from that point on, you can derive every physics that you encounter in special relativity and all the physics and effects that comes out of it. But when you go from the idea of 4 position, 4 velocity, there is a natural reason as to why that is the case. Okay, that's good. Now, next is, now we have velocity, we have position. Now do acceleration, right? So that's the next step, and let's do that. And after that comes the force, and that's it. Okay. So we have again U alpha. Let me remind ourselves of U alpha, which is C times gamma times velocity times gamma. Gamma itself is 1 over 1 minus beta square. For momentum was mass times this quantity, but now we are defining acceleration. Right. So acceleration is going to be defined as same, right? We said derivative of position was velocity, but derivative with respect to an invariant distance. And here we will again say this is du alpha over ds, but that doesn't have the dimensions of acceleration, so we multiply by c, right? That's velocity divided by distance, so you want to multiply by c so that you have velocity divided by time. Right? So that's good enough, and you suddenly see that this will suddenly get complicated, right? So let's see what this becomes. Let's do this. So this is dt over ds times d by dt of c times gamma. Let me pull out the c, and that's my gamma. And now I can multiply by gamma or by velocity, right? So let me write that as c times d by dt of beta times gamma. And this structure also plays an important role when we talk about uniformly accelerating particle. That will play an important role in that particular scenario. So keep that structure in mind. Okay, so that seems like a lot of work, right? Time derivative of gamma is having a square root in it. So yes, that will involve some work, but certain things we can take care of. dt by dt, this quantity we know, right? That's your gamma, right? That's your gamma. So this simplifies a little. So that's gamma times c, or c times gamma I can pull out. So, right? So c comes out, and you have d gamma over dt and d by dt of beta times gamma. Actually, since we are doing this, let's do this explicitly. Let's expand this out. That'll be two pieces. So that's d beta by dt, right? That's a v over c. So that's 1 over c times acceleration, right? When I hit the velocity, I get the usual Newtonian acceleration. This is a Newtonian acceleration plus, or times gamma. So gamma stays as it is, plus keep the beta as it is and multiply by d gamma by dt. Right? One cannot help it, so it's a little clutter in there, but you do see one thing, that if I were in the rest frame, so rest frame has some features associated with it. At least in one frame, if I were to go, this goes away, gamma goes to 1, but then still, what about derivative of gamma with time? That seems to be not very clear. So we need to evaluate that, right? So that's the next goal. So we have to get a clear picture of what this acceleration structure is, we have to evaluate the derivative of the factor gamma with respect to time, but we will use a trick to do that, right? So this is your acceleration. So let's digress a little. So let's keep this as it is, right? And we'll come back to this in a few minutes. Let's go back to u alpha, right? And remember that u alpha is space-like. So this is a trick I'm going to use to evaluate this quantity, derivative of gamma with time, right? So this is an identity. We showed that earlier, that the length of the 4 vector is, or the square of the length of the 4 vector is a negative quantity, and it is a square of the speed of light, right? If I were to take a mathematical derivative with respect to s, I do get u alpha, so that will be two symmetric things. So this is du alpha over ds times u alpha. This is acceleration, right? Or I can hit the other quantity, right? So this is u alpha times du alpha over ds. That's equal to, speed of light doesn't change with respect to any of these quantities, so that's equal to 0. That's acceleration showing up, right? So that's acceleration a alpha u alpha. And in your homework, you work on the fact that whether it is a alpha, u alpha, or a, it doesn't matter whether you're multiplying contravariant with covariant or a covariant with contravariant. Those are the same quantities. Those are just labels. It's a matter of -1 sign, whether you put it in the first vector or in the second vector. You can easily immediately say that these two are actually the same quantity. So it is 2 times a alpha u alpha is equal to 0. A 2 factor of 2 doesn't matter. So that's equal to 0. Okay. And the first problem in your homework deals with the fact that, so now this is a time-like quantity, right? This is a time-like vector multiplying another vector to give you 0. Okay. What can you say about the other vector? So, so what we are having is that this quantity is equal to 0. Now, I can evaluate this quantity in any frame I want to. So here is how I will prove it. So let's go to the rest frame, like choose. So this is a true statement in any frame. So this quantity in the rest frame of the particle. Rest frame of particle. Because I know what u alpha looks like in the rest frame of the particle, so this will be a0, right? u0 is simply c, or I don't even have to go there. In the rest frame of u, let us say, so in a so this, since it's a time-like vector, there exists a frame in which it is purely time-like. Like it has only a time-like component, so that's 0, and plus this is 0, a I, if you want, times 0, that's equal to 0, which means to say that this quantity is 0. Is that clear? So this is a typical, very typical argument you use in relativistic or relativity ideas. This is new. We don't usually use this in Newtonian physics. I shouldn't say we don't. It is possible, but it is not common to do that. Relativity principle, basically go to a frame, make an argument, and then come back. So what we are doing here is that we are choosing a particular frame in which this is purely time-like. In that particular frame, this is true. If this is true, since u0 is not equal to 0, this implies that a0 is equal to 0. Because u is not 0, it is time-like, right? It cannot make it 0. So acceleration 0 component is 0. That means to say that in this particular frame, this 4 vector, the a alpha, looks like 0 and ai, whatever that is. That means to say that this is a space-like vector. Is that clear, the arguments that I've used in here? So I started with this identity, saying that there is a time-like vector multiplying another vector is 0. That means to say that I can go to a time-like, I can go to an inertial frame in which it is purely time-like. That means there is no space components in there. That means this statement should be there. If this is true, that means that 2 quantities multiplied is equal to 0. So the 0th component of a is 0. That means to say this can be written in this form. That implies that a alpha is space-like. So then I can release that whichever frame I am in. Once it is a space-like, it remains a space-like. You can never change that property. Like it's an inertial frame independent quantity. So that's a space-like. So that means to say space-like and time-like is orthogonal. Like that's an orthogonality statement, right? In Lorentz frame, in the Lorentz idea of orthogonality. Orthogonality is not like the usual orthogonality that we have 90 degrees there. That's not the way it works. In the Lorentz frame, it's orthogonal in the sense that if you multiply this vector with that vector, you get a 0. So A alpha is a is a space-like quantity, right? So that's a good information to have, and that means to say that basically whenever we have an acceleration, we will go to a frame in which that is only a pure space-like component, and that will be called a proper acceleration. So we won't be able to talk about uniformly accelerating particle, but what we can talk about is what is known as uniformly properly accelerating properly, or a particle moving with uniform proper acceleration. That means to say that in its own rest frame, it will be at rest locally, like locally at every instant of time, it will be at rest. And we'll talk about that. That will be the main idea we will work on next class. But here very quickly, let me evaluate what is d gamma over dt, right? So let's change both space. And we have u alpha is equal to, or let me say a alpha, right? A alpha. Right? A alpha is, we just now evaluated here. So this is c times gamma times d gamma over dt, comma c gets cancelled, so then there is a times gamma square, and then there is plus c times beta gamma d gamma over dt, right? So a little bit of algebra now. Let's say u alpha is equal to minus c gamma times v gamma. V gamma. I cannot write gammas. Okay, gamma. If it was a superscript contravariant vector, it is plus c. It's a covariant vector, so it is minus c gamma. But a alpha is 0, right? So a alpha, u alpha is equal to 0. So that's easy to calculate. So just multiply this. So that's minus c squared times gamma square times d gamma by dt, and these two have to be multiplied. A dotted with v, so this is plus a dotted with v, dotted with, and then there's a gamma cube, right? So there's gamma cube, and this has to be multiplied with this. So this is plus c square. I multiply by a c and divide by a c so that it becomes a beta. So this is beta, that's beta square. And then there is a gamma square and d gamma by dt. Okay. So dimensionally, it has, each one has a dot a acceleration and a velocity. There's c square and a time. There's a c square and a time there, right? That's nice. So let's take this onto the left-hand side. So that, and so we have c square, and that is 1 minus beta square. And then there is gamma square, d gamma, d gamma, right, by dt is equal to a dotted with v times gamma cube. Gamma square and 1 minus beta square is just 1. Right? So that's nice. So that goes away. So that's equal to 1. So this way of calculating avoids a little bit of algebra, but still there is a reasonable amount of algebra here also. That allows us to calculate the derivative of the factor gamma with respect to t, which is coming in our acceleration, right? So this is c square and gamma cube. The factors of gamma is what decides how. So gamma is the kind of a characteristic of a certain parameter in relativity. How it changes with respect to inertial frames decides how quickly things are changing, like position contracts, but velocity contracts with another set of gammas. Acceleration, we will see, comes in different forms. Sometimes it is gamma squared, sometimes it's gamma cube, and we will talk about that later on. But let's go back and at least write acceleration. I have a minute more, so I'll use that, and I can put that back in the acceleration, right? So yeah, this is the expression for acceleration. So I have an expression for acceleration in terms of velocity and acceleration alone. So that's equal to, so it is, so this can also be written as 1 over c times beta dotted with acceleration, right? Times gamma cube. Right. So if I were to use that, this becomes gamma 4, right? So this is beta dotted with acceleration times gamma 4. That's a 0th component of acceleration. It's not as clean to visualize as velocity was. There's a dot product and all coming in, but it plays an important role. And then there is acceleration itself times gamma square. That's what here it is. And then we have a component parallel to velocity. So acceleration has a component proportional to acceleration itself, but it also has a component proportional to velocity, and that is plus, so now gamma times gamma, so it's beta gamma. So it's beta times beta dotted with a times gamma raised to 4. Right? Did I write all this correct? Hopefully. Correct me if I missed something. Yeah, so that's your expression for acceleration. One thing is very clear. So the easiest one can see in the rest frame, right? Always rest frames are nice. In the rest frame of the particle, right? This is, and by the way, by rest frame of the particle, this came up in a discussion in the other class that, of course, it means that you're at rest with respect to the particle, but you can only be on one inertial frame at a time, remember, right? So if a particle is accelerating and you want to choose an inertial frame, you have to keep jumping from one inertial frame to the other. If a particle is accelerating, it is not possible to be in the rest frame all the time. So by definition, if you're in a rest frame, you are jumping from one inertial frame to the other inertial frame. So that leads to the idea of a local inertial frame. Local inertial frame means at an instant you are in an inertial frame. In the next moment, if you're in the same, if you're sitting on the particle still, you have changed your inertial frame. So you have to use your transformation properties to go from one instant to the other. So that's a complication that comes in. But with that idea that rest frame, beta is equal to 0. So that's equal to 0. And that's acceleration A. Whatever this length is, right? So let me. So this quantity here, the length of A alpha in any frame will be the same as the length in this particular frame also. So A alpha rest frame square, right? Magnitude square. I should write A alpha and A alpha down, but instead I wrote it like that. And that will be equal to this particular, so let me call it A0. So just to differentiate it from this A, since this is a particular frame, that's not the usual acceleration you would measure here. So that's A0 square, right? And this is called the proper acceleration. This length being an invariant quantity will remain the same in every frame. So it is natural to ask, what if there exists a particle, imagine a hypothetical particle, which goes with a uniform proper acceleration. At every point in its journey, it keeps its acceleration, this quantity, the same. What is such a particle? Like, how would it move? What is the curve that represents its particle? That's the idea of uniform acceleration in relativity. There is no idea of normal parabolic uniform acceleration. This is the idea of the uniform, closest we can have to uniform acceleration, that it is going with uniform proper acceleration in the sense that this distance remains the same. And what is such a particle physically? If you put a charged particle in a uniform electric field, it will have this property that it will behave with, it will go with uniform proper acceleration. This is also called Rindler acceleration. So Rindler went ahead and talked about space-time associated with this. So Rindler played a good role in this. Rindler coordinates, if you want, Rindler acceleration. So these are all words that you can use to check it out. But proper acceleration is just proper acceleration is good enough. I will stop here, and next time we'll talk about actually a force, force. That's the only thing remaining at this point, but that's a small extension of this. Write down the equations of motion and talk two things. One is what happens if something is going with in an electric field, and what happens if something is going in a uniform magnetic field. And I will also talk about like this acceleration sometimes, since it has a velocity directional component and an acceleration directional component. What if velocity is perpendicular to the acceleration? What is the kind of motion? What if velocity is parallel to acceleration? What is the kind of motion? So those will be the two distinct motions we will talk about. And I'll stop at this point. Still, I took 6 minutes more.
I have a question regarding the first
Yes.
work. There is a term called future pointing or past pointing. What does that mean?
Future means delta t is greater than 0. The usual Newtonian change in time is greater than 0. If you want to see it in space-time diagram, so this is your let's say x, and this is your c times t, correct? A vector of this kind, that's also a space possible vector. So let me call this 1, and this is also another vector possible, right? So when it is pointing in the upward direction, it doesn't have to be really upward. It can be inside a cone also. As far as it has a positive time component, then it is future pointing. Okay, is that clear?
Otherwise, it's past pointing. The one
Otherwise,
that's down is past pointing.
Exactly. Or else, let me put it like this. So if I have A alpha is equal to A0 and A vector A, right? If A0 is greater than 0, correct? Then you would say it is future pointing. Okay. And A0 greater than 0 has a meaning only if it is a time-like quantity, time-like vector. If it's a space-like vector, A0 greater than 0 has no meaning. Okay. Is that clear? And you, for working on those problems, work on the arguments that I worked here when I proved starting from A alpha U alpha equal to 0, I proved that A alpha is space-like. Like I basically went into a frame in which it is purely space-like or time-like. So all those problems can be worked out by going into a frame where it is purely space-like or time-like, and then make some arguments there and then come back. Okay, so that's a hint. Otherwise, do it your own way, but that's the easiest. That is very clean. In 3 steps, it comes out usually. Okay.
Yeah.
Any other comments, questions? Last week, you guys are exceptionally quiet. Okay. Should go and get work done then.
Yeah, I have a lot of work to do this week to get caught up.
Yeah, understandable. Same thing here.
I still
I
have to
lost
watch
about-
videos for 2 of my courses.
Watch videos. Okay, yeah. You keep delaying, right? That's understandable. Yeah. Yeah, I can say that I too lost a lot of time because of this website thing. It took some time to get this stuff.
For quantum mechanics, Professor Mazumdar used to upload like lecture videos before class, and we used to have a live class session where we talked about what the lecture videos were talking, like what he was saying in the lecture videos, and I never watched lecture videos.
And now that has stopped, is that what it is?
I don't know. He stopped.
Yeah.
Now we just have live,
Only
live
live.
session.
I see.
Yeah.
Yeah.
So which is good for me.
Yeah. I also started that way. I mean, I thought that I will have to make on the whiteboard and then come and present here, and there will be recordings. But then I was very happy that I didn't have to pre-record it. That saves a lot of time.
And
Making it spontaneous is a lot easier than doing it on
So
your
it
own.
looks like next semester might be a mix of online and actual classes.
Really?
That's what the last email from the chancellor was, right? Or dean, I don't know. There was an email.
No,
which
he
said-
didn't say anything. He said we are going to be considering, but he didn't say anything. Correct?
Oh yeah,
If
I mean, I
read
would
it.
assume considering probably means that it's going to be like that, you know? Chancellors.
Hopefully not.
we have
Hopefully
more
not.
than 3. We have more than 3 months to decide.
Yeah, they have less than that. I think they have to decide by a month or so, I think, because all the enrollment and all that, what is that called? Registration processes begin earlier, I think. So I think they still have a time. It is not like March when they had to decide in a few days. So they surely have time. But hopefully it is not online. I don't like it. I think you guys also don't like it. And I think it will hurt the enrollment. Like students might not come. I mean, they will say that we are better off not registering for this semester, maybe. I don't know how students think. Yeah, I don't know. Let's see. It's not in my hands.
I don't think
Hopefully
that
it's
way.
not what Angela says. I wouldn't like it.
I don't think
At
that
least I
way. I
don't.
just want to graduate ASAP.
Yeah. True.
Yep.
Yeah, I'm fed up being an undergraduate student.
You'll be surprised.
Exactly.
Those are the best times. Yeah.
Okay, I was just working out that problem that I asked right now, and I don't. Can we just go through it right now? I think it's
Okay.
if I think it's 1B. I thought it might be a straightforward problem, and it's not kind of coming. So if
Yeah, that's
P mu and Q mu are both time-like vectors.
Let's see.
And
By the
one
way,
is
if any of you guys want to leave, you can. Okay, so don't feel compelled that all of you guys keep staying. So now we're just having homework discussion, but this probably will help everyone. So this should compel you guys to stay too. So what was the problem? Remind me. Okay. Yeah, you were trying to say yes.
1B. So P mu subscript and Q mu superscript, two different vectors. That's
P alpha,
subscript.
Q alpha, right? Okay.
So yeah, okay. I mean, P is the downward and the Q is the upward.
Yeah, it
P
doesn't
is
matter.
contravariant and doesn't matter, right?
Yeah, it doesn't matter. Yeah. Okay.
So it's saying both are time-like vectors.
Both are
and
time-like. Okay.
their
So
product is positive,
is greater than 0. Right.
then either both
And
are
P,
future pointing or both are past pointing.
so P and Q are time-like, right? Time-like,
Yeah.
let's say. Okay.
I think.
So again,
I think
yeah, go ahead.
for that to be 0, one has to be negative and one has to be positive, right? So
It's not 0, it's positive, right?
So the contravariant.
Yeah, so it's like saying P and Q are like just some P0 and 0 and Q0 and 0, right?
Yeah.
Yes, exactly.
And
so let's say,
Or
so this is what is, yeah, keep going. Yeah, you want to say, keep going. Yeah.
So that product is basically like minus P0 Q0 form, right?
Yeah, so suppose I were to write this. So P alpha is equal to P0 and P, right? And Q alpha.
So if you say they are time-like, doesn't that mean P is 0, P vector?
It is not 0 all the time, but I can go to a frame where it is 0. That's the point. Yes.
Oh, okay.
Like it is not in general 0. But it's a time-like means that I can always go to a frame where this is 0. That's the idea. Same thing I can do with this. Right? There exists another frame where this can go to 0. So suppose I go to that. So in general, P alpha, Q alpha will be equal to this with a minus sign, right? So this is minus P0, Q0. Notice this could be a little confusing. This is also equal to minus Q0, right? I can write in various forms. This is, if I write it, subscript 0 is different from superscript 0. It changes sign, right? So I'm going to keep superscript all the time, so then the negative sign shows up. And plus P dot Q. In general, this quantity is always equal to this, and this is invariant. Okay. This will stay, actually, this is not invariant, this is covariant if you want. Right. Now, I can always go to a frame in which this is equal to 0. That's the idea of time-like vector, right? I can go to a frame in which this is 0, right? Go to that particular frame in which it is 0. So this is now not really equal.
I'm sorry, is it that supposed to be Q superscript? I thought it's subscript. If you're taking the minus sign, shouldn't it be subscript?
I did change
Q0?
Oh, because
in the next line.
This is Q alpha, notice. This is subscript.
Okay, and the next term, Q0. Q0, what happened? Why is it a superscript?
Okay, so let me write one more statement. Okay, here. Q alpha is equal to minus Q0, Q. Correct? Which is also equal to plus Q0, Q0, Q. So I'm multiplying this vector and this vector, correct?
Okay.
Up and down. I'm not multiplying these two. I'm multiplying
why not?
This because it's a.
Oh, okay.
Right. Always when you take a dot product, it is one with an upper and one is a down. Right? Contra always multiplies the covariant. That's the way it is defined.
Okay. Yeah. Okay. I get it.
We have skipped those kind of steps, but we have taken it as a prescription here. So one can go in detail and why we do that. That's all is different. Okay. So this is the definition. If you want the superscript or the contravariant multiplies the covariant, then we are multiplying these two quantities, not these two.
Okay.
Right. That definition exists, but it is these two. Okay. And then you have a choice. So this is in general true. This equation is in general true. Then you have a choice to go in a particular frame because this quantity is going to stay the same in every frame. So I can choose this to be equal to 0 and then argue. Okay. And then you will be able to say, oh, this has to be greater than 0, less than 0, or something like that. Okay. Because this is.
Term is, that's where I was confused, because if that is positive, then we would have either want one of them to be positive and the other one to be negative, right?
Exactly.
Then
That's
both are future pointing or both are past pointing. That means it needs both to be positive or both to be negative, right? That is kind
that's
of
correct.
what I thought that was.
You're almost there. You're almost there. Just put it together.
I am getting the idea that one is future pointing and one is past pointing and vice versa.
Yes, so Q alpha is greater than 0. So this has to be greater than 0, right?
Yeah.
And this is, one of them can be chosen to be 0. So this is 0. So that's minus P naught, Q naught is greater than 0. Correct? And that means to say, I suppose that I can, if I switch the sign, I switch the greater than sign, I guess. Right? 0. So if this has to be 0, one has to be future, one has to be past, right?
Yeah.
So this is P0 greater than 0 or Q0 less than 0. That's one possibility. Or there is another possibility that P0 less than 0, Q0 greater than 0, right?
Yeah.
So that's the two solutions.
Okay, the question says prove that either both are future pointing or both are past pointing.
What?
So according to the condition, minus P0, Q0 is greater than 0. So if you have one towards the past and one towards the future, that means you're gonna get P0, Q0, right? P0, Q0, according to our definition, it is smaller than 0. So that means so we don't get a time lag. So that condition does not satisfy our given condition. So if we say both have the same sign, that means we're gonna get negative sign in here. So according to the given condition, it is greater than 0. If you can
hold on, what's the question? I'm not seeing the, give me a second, okay? Let me see. Okay, if we are both time-like vectors and then either both, so we haven't used the fact, right? So okay, so the question is saying that P mu both are time-like. No, we did use. Okay, sorry.
So we have to use
either both are future pointing. Oh, so you're saying that the conclusion we are getting is wrong.
Is wrong. That's what I kind of looks like.
Oh, I see. That's your question. Okay, I almost got it. Okay, let's see. So what's wrong here? Help.
I don't think anything is wrong here. We just have to use. We just have to use this first, second, third, fourth line where we say minus P0, Q0 plus P dot Q is greater than 0. That is a given condition.
Oh no, it's not greater than 0, right? It is less than 0 if it's time-like. If it is time-like, it is less than 0, right?
The given condition is that it is positive.
Okay, sorry. Yeah, okay. So
for us, negative is greater than 0.
Oh, yeah. Actually, and both are future pointing or both are past pointing.
Does it
no.
matter how because it says P subscript mu and Q superscript mu are time-like. So then you have, if you...
No, that doesn't matter. That doesn't matter. Because that, I mean, whether it's covariant or contravariant, it doesn't change the nature of time-like. Okay, so here is the point.
But the sign will come into picture, right?
No, most probably this is an error in the question. And that's because, remember, different textbooks use different signs. I use position to be positive and time to be negative. In this class, is this clear what I'm saying? In our ways of doing it, we are saying this is equal to, or the best way to say this is that time-like means less than 0 time means less than 0 and space means greater than 0, correct? I think since this is a problem taken from a book, my suspicion is that in their book, that's off by a sign. Because otherwise, this is a straightforward conclusion, correct? I don't see any mistake in that. So let's not try to change the arguments to fix the answer, okay? Go by what you're getting. Don't go by what the answer is wanting you to get, okay? Use your judgment and get the right answer, or change the question accordingly. Believe your derivation than the question, okay? And I will try to get this actually, I can, advantages of being at home, I have the book right in front of me. Let's see. Houston and Todd. And does it say which problem? No. No, I have to search for it. Yeah, the metric is different here. The metric is bent towards time. Time is positive in this book. And then they write if P and Q are time-like and P times Q is greater than 0, then either both is, yeah. So I think this question, I made it a long time ago when I was using this book and this metric. So here is a point, as a conclusionary statement, there's a typo in problem 2A. Thank you for bringing this up. So problem 1B, right? There is only one greater sign in that. So the greater should be switched to less, okay? Is that clear? Sorry about this. Problems with copying a problem from a book. Okay. So change the greater sign to less sign, and then you will be fine, Angela, correct?
I think so.
Good point. Yeah. Okay. Avinash, does that work with your arguments?
Yeah, my argument works anyway.
Anyway, it works anyway. You can get any answer.
All I was saying was I force my argument that minus PQ is greater than 0, and according to that I can proceed. But if it is smaller than 0, it works even then.
It shouldn't. Yeah. Okay. I won't. It shouldn't. Because if it is less than 0, then you would come the other way, right? Yeah, think about it. Yeah. If there was an exam, I would have put this question in the exam. That was a very good, after this much of discussion, that would have been my favorite question in the exam, but we don't have a final exam. Yeah. But clear, right? Sorry about that. My fault. And thanks, Angela, for pointing out. Thanks, Avinash. Yeah. Okay.
All right. I'm gonna sign off. Thanks, guys.
Yes. Yeah. Take care. Yeah.
Yeah, you
One more
too.
week, right? Or 2 more weeks. I think after that you will have.
I don't actually know when our quantum exam is. I forgot. Do you guys know?
Dr. Bird said sometime around 6th or 7th, I think, something around that.
Okay. Yeah. All right. All good to know. Cool.
Okay.
All right. Toodaloo.
Bye. Enjoy.
Bye.
Bye.
Bye, Jordan.
Have a great day, everybody.
You too, Avinash.